All right, welcome back to another episode of Math with Sohn. Today we're going to be continuing AP Physics 1, and we're going to be talking about relative velocity and frames of reference. Frames of reference are something really easy, but often very confusing to understand. It relates to how you are perceiving something if you were put into a specific spot. So a reference frame is a coordinate system that is fixed on a single point, and that point can either be moving or stationary. Okay, for instance, if you are in an airplane flying 580 miles per hour and somebody brings you some food, a tray of food, that food doesn't appear to be moving to you. That food appears to be stationary, so you can grab whatever you're eating, the piece of steak with a fork, and you can eat it, and it's not moving 580 miles per hour to you. It looks like it's stationary. But to somebody on the ground, they don't even see the steak, but that plane looks like it's moving in the sky quite fast. Okay? So relative velocity, we got some cars here. From car A's perspective, they are going 65 miles per hour to the right. And from car A's perspective, when they look at car B, because car A is going 65 miles to the right and car B is going 70 miles to the left, from car A's perspective, it would appear that car B is approaching them at 135 miles per hour, which is way faster than what they are going, because from their perspective, they're not moving. Everything in their car is stationary, and everything outside the world, it looks like, is approaching them at 65 miles per hour, which is a very weird thing to think about. If you even think about it from car A's perspective, even though they're the ones moving, everything around them looks like it's approaching them. So it really looks like car C is approaching car A at a speed of 65 miles per hour, even though car A is the one moving. Car A is having everything approaching it from its frame of reference. Okay? Now for car C, everything is moving around them, and that would mean that it makes sense. The car A is approaching them at 65 miles per hour. Car B is approaching them at 70 miles per hour. But car C, everything inside of it, even though they're not moving, would also continue to not move, because objects at rest tend to stay at rest according to Newton. Okay? So that is frames of reference in a nutshell, but we got some more examples for you. Example A, let's move that paper out of the way. Example A, you are sitting at the back of a bus on a field trip. The bus is traveling 30 meters per second. Your teacher is walking towards the back of the bus at a rate of 4 meters per second to yell at you for acting like a schmuck. Find the velocity of your teacher relative to the ground. Relative to you, the teacher is approaching you at 4 meters per second because you're both on that bus. But relative to the ground, the teacher may be moving on this bus at 30 meters per second. Here's the teacher. And they are, because they're moving on the bus at 30 meters per second, but because they're walking backwards, that would be counteracting the speed of the bus, and you would have 30 and take away 4 moving in the negative direction because it's moving to the left, and their actual velocity would be 26 meters per second, which kind of makes sense. All right? The student sees the teacher approaching them at 4 meters per second, but the teacher is actually moving 26 meters per second in the opposite direction with respect to the ground. Okay? Next example. A cowboy is riding on top of a train. So this can be similar to a train here. And it is moving. I got a better, cool little picture on the other page. Cowboy on the top of a train. He throws his hat in the air out of joy, and then he catches it as it is falling back down to the ground. The trajectory of the hat is what we want to draw, but we need to draw it from different frames of reference. If we think from the cowboy's perspective, the cowboy fixed to the train, with it being he is also fixed to the train, that hat appears to go straight up and then straight back down. But if we think about it from a frame of reference where there is an observer watching the train as it passes, well, then that hat would appear to go up and down while the train is moving. So from them, when you think about it, the hat went up and then it went back down, but because the train is moving this way, the hat would appear to have this arch. And if the observer was walking in the opposite direction, that train would appear to be moving even faster, and that arch would get even bigger, which is kind of neat. Okay? And we can use these ideas of frames of reference to create triangles, which can then be used to use trigonometry, sine, cosine, tangent, and the Pythagorean theorem, which will happen in our next example. So, an airplane drops a bomb on a target. Congratulations, you have just blown up something. Hopefully, there are no people involved. At one particular instant, the bomb is falling at a rate of 20 meters per second directly below the airplane. That is not accurate in terms of physics. Physics would have kinematics and it would be falling with acceleration, but it says at one moment. At one particular instant, okay? That's a very important detail because it's one instant. At one instant, it might be falling 20 meters per second. The next, it'll be falling faster because of gravity's acceleration at negative 9.8. An observer on the ground sees the bomb moving towards the ground at an angle with a speed of 80 meters per second. We want to know how fast is this airplane flying with respect to the ground. Okay, so we need to draw a picture here. First off, bomb is going down 20 meters per second. Then we have a bomb moving towards the ground with an angle with a speed of 80 meters per second. So that would be, so to speak, the hypotenuse, 80 meters per second. And we want to find the speed of the plane. Well, the speed of the plane can be done one of two ways. You need to create a rectangle. This is the plane moving horizontally in the air, which would be the same as if we went this way by writing plane, or you could also think of the 20 there. You create like a rectangle. With that rectangle in mind, I'm going to redraw it over here. We got the plane. We have the 20 meters per second, even though it got dropped over here, and it's kind of curving down like this. With one instant, it would be straight. And we got our 80 meters per second there. We want to find the speed of the plane. Because both of these are in velocity, you can just use the Pythagorean theorem to find the velocity of the plane. As long as the units are aligned, you can use Pythagorean theorem. Even though it's not distance, you can use the Pythagorean theorem just to solve for velocity, which is a really neat feature. If we do that, we'd have 20 squared plus the plane's velocity squared, because this is the hypotenuse, that's your c, would equal 80 squared. And we solve for that, we end up with VP squared would equal the square root of 80 squared minus 20 squared. Solving for, wouldn't be squared anymore, I already square rooted. Solving for the velocity of the plane would give you 77 meters per second. And that's going to do it for this one, everybody. Until next time, stay positive, and I will see y'all later. Bye.